In this video, we're going to explain sign extension for 2's complement numbers and why it works. First of all, let's recall that the 2's complement number system is a convenient notation for integers, both positive and negative. An integer is represented in 2's complement as a bit string, interpreted as a binary number in the usual positional notation, but with one twist. The high-order bit is given negative weight. In 2's complement, any bit string in which the high-order bit is 0 represents a non-negative integer. Any bit string with a high-order bit of 1 represents a negative integer. For example, consider the following two 8-bit strings. In the case of our first number, since the high-order bit is a 0, we treat this as a positive binary number using standard positional notation. Counting from the right, it has 1s in the 0th, 1st, and 3rd bit positions. That means that it represents 2 to the 0 plus 2 to the 1 plus 2 to the 3, or 11. In the case of our second example, since the high-order bit is a 1, this represents a negative number. Again, we use the standard positional notation, but the high-order bit, which is in the 7th bit position, has negative weight in this case. Hence, this represents 2 to the 0 plus 2 to the 1 plus 2 to the 3 minus 2 to the 7th, which is 11 minus 128, or minus 117. Now suppose that we needed to store one of our 8-bit numbers into a 16-bit container, such as when assigning a char to a short in C. We'd like to set those extra 8 bits in such a way that we don't change the value of our number. It's clear that if the number is non-negative, i.e. if the high-order bit is 0, then we can just pad the number on the left with zeros. For example, our first number is sign extended into this. Clearly this doesn't affect the value. The only really interesting case is what to do if our initial number is negative, i.e. if the high-order bit is 1. The claim of sign extension is that you can pad such a bit string on the left with 1s without changing its value. For example, our second bit string, which represents a negative number, is sign extended into this. When interpreted as a 16-bit 2's complement number, this should have the same value as our original 8-bit 2's complement number, namely minus 117. Of course, we could verify that for this specific example using our 2's complement evaluation rule. But trust me, it evaluates to minus 117 as expected. But let's argue that it works in general to do this type of sign extension on negative numbers. Let's consider an arbitrary negative 2's complement number in W bits. Any such number will have this form. That is, there will be a leading 1 followed by W minus 1 other bits. For convenience, let's abbreviate that as follows. Here, B is the bit string except for that leading 1. According to our evaluation rule, all of the bits in B have positive weight, so we can just treat those bits as representing some non-negative integer value x. Finally, we note that the leading 1 has weight minus 2 to the W minus 1. Hence, our 2's complement negative number 1b represents the integer value minus 2 to the W minus 1 plus x. Now consider what happens if we prepend a single 1 onto the left end to give us the sign extended number 1b. We need to show that this W plus 1 bit 2's complement number has exactly the same value as the W bit 2's complement number 1b. Following our familiar rules for interpreting 2's complement numbers, bit string 11b has value minus 2 to the W plus 2 to the W minus 1 plus x. But a little bit of algebra shows us that this is equal to minus 2 to the w minus 1 plus x. Here's the algebra for those who are interested. This shows that adding a 1 to the front of our bit string doesn't change its value. And since our initial value was an arbitrary 2's complement negative number, we could do this to any negative number without changing its value. Moreover, if we can do it once, we can do it twice, 3 times, etc. This shows that sign extending a negative 2's complement number doesn't change its value. Recall that we argued earlier that sign extension is obviously correct for non-negative numbers. This suffices to show that sign extension does not change the value of any 2's complement number, which is what we set out to demonstrate. By the way, we could have made this argument more formal as a proof by mathematical induction on the length of the sign extension. We'll leave that as an exercise for the mathematically inclined viewer.